So thanks for joining me on our tutorial on vector calculus. So essentially the motivation on it is a long lecture is that we need to give you the mathematical tools so that we can understand how we can operate and how we can introduce the Maxwell's equations in the upcoming chapter. So even though it may look complicated, and of course it is complicated that when we're dealing with vectors, there's no way around this. And of course, we should actually, in fact, embrace vector algebra and vector calculus so that we could really generalize our description as we need to do. So what we will be doing here is that I will be introducing to you the first algebraic properties of vectors. So how do we add them together? How do we multiply them together? And what kind of properties they have? And after that, I will be talking a little bit about the vector calculus. So how do we differentiate vectors and what kind of operators we have when we are doing this kind of vector-based calculus. So lots of things to be going through, and I'm pretty sure that many of these operators will be new to you. So please bear with me. But on the other hand, there's no way around. So you should instead think of these new entities as your new close buddies and friends instead of enemies. So this is what I want to say in order to motivate the lecture, and let's now get started. So let's look back into how we can add, how we can subtract vectors together. So what are their algebra that they form, and of course in the end we are interested in the fundamentals of vector calculus so that we could understand the Maxwell's equations, so that we could form differential equations and we could form a wave equation based on them, and then we could see that in fact these wave solutions and mathematical waves we have been treating already, they actually arise from the Maxwell's equations and the wave equation formed subsequently. For peace of mind and simplicity, we restrict our treatment to the Cartesian coordinate system, but of course the same kind of rules would apply in other systems, but it's way easier to just restrict to the Cartesian coordinate system. And we start here by defining two complex numbers, a and b, and complex valued vectors u and v. And u, we are interested in the three-dimensional space. So u has three components, u1, u2, and u3. And v vector is another vector we need to introduce, and it also has three components inside it. So v1, v2, and v3. And we need to form an algebra for vectors. So of course they have these algebraic properties. So when we are adding two vectors together, u plus v, we can just add the different components together so that the u1s plus v1 can be added together, and then u2 plus v2 gives me the second component, and so forth. If the sub indices 1, 2, and 3 seem obscure to you, please just replace them with x, y, and z yourself, and this is how you could get the end result. But using summing notations, 1, 2, and 3 are easier indices, so that's why I prefer using them instead of x, y, and z. So this is the addition, summing up of vectors together. We can also multiply vectors with scalars. So we can take these two complex numbers and we can sum them together and we can multiply that with the vector. So this kind of operation will be dealt by just multiplying our vector v with the original first complex number a, and then we are summing into this a vector v that is multiplied with the second complex number b. So this is known as the scalar multiplication, and this is how it's being done. Then we have this operator that we can also multiply two vectors together, and there are two different ways of doing this kind of multiplication. The first one results in a scalar and is also known as a dot product, as shown in the slide right now. And here what we do is that we sum the different indices together. So we sum the different components together and we multiply the different components. So we multiply u1 with v1, and that will be giving my first term, and then I'm summing this with the u2 times vt term and then the u3 times v3 term. And this is known as the dot product or scalar product. And here, as you can see, if we would have it had indices of x, y, and z here, it would have been more complicated to describe the summation. To me, at least, it's easier to just have 1, 2s, and 3s in there. And then we have another type of a vector multiplication, and this time actually this ends up in a vector. So we have also a cross product, or also known as a vector product. And here I'm just defining this using the geometrical definition for the vector product. So I'm multiplying the amplitudes of these two vectors u and v together, and then I'm calculating the respective angle, sine of theta, and the new vector points along a normal from the plane defined by these two vectors. So n is the normal of the plane defined. So this is a cross product, also known as the vector product. So I have my two vectors, u and v here, and they are defining my plane. And I'm having the sine of theta. So the theta angle is the angle between or with respect to these two vectors. And then I have my unit vector that is pointing perpendicular to the plane defined, spanned by these two vectors u and v. So that the vector n here, n hat, is here, exactly this guy here. And sine of theta, the theta here is the angle. And if the u and v would be pointing along the same direction, the theta angle here would be 0, and we can then see that this term of sine becomes 0, so that the cross product of two vectors that point along the same direction is identically 0. So this is the kind of nice thing that we already see from this graphical representation of the cross product. Similar thing happens with the dot product, so that if the two vectors are perpendicular, then we will have always 0 from the dot product. And this is a nice thing because we can have a kind of geometrical or graphical interpretation of these two different kinds of products. And we are using them all the time when we are doing vector calculations. So the dot, or also known as the scalar product, and the cross product, also known as the vector product, they can be compactly also represented in different ways. And here, for the peace of mind, I'm showing you Einstein's summing convention. Most of you probably think that this is way beyond our course curriculum, and you would be entirely right. But I want to introduce to you this notation, because if you ever are wondering about these strange vector identities that we will be introducing shortly to you, and you would be wondering that who on earth was deriving them in the original place, then I would say that everybody can do the derivations, and everybody can do them quite easily using the Einstein's summing convention. So this is my motivation why I'm introducing you this notation. We do not need to use this notation in our course, and you do not need to use it, but at least you have been informed that there is this kind of convention, and this really would help if you would want to deal with this kind of derivation of vector identities, so that you could really see and verify yourself that they make sense, what we will be encountering next in the lecture. So using this summing convention, we can also write, for example, this dot product very easily, as we already encountered. It's calculated by summing the different components together, so ui's times vi's. And the Einstein's invention here was that since we have 2 times the index mentioned inside the sum already, we have 2 i's in here. Actually, writing this summation here is quite redundant. And in fact, we can just skip this summation here entirely, and we can just write this term as a 2 i's. What I mean here is that we can just write this simply as ui times vi. And this is known as the Einstein's summing convention. So whenever we have 2 indices that are same indices, we do not need to write the summation out, but we can just skip it altogether. And we know that implicitly this kind of notation means that we must sum over all the indices. And this is how things work. So it's not explicit notation, so we are hiding the summation, that we are not showing it at all, but of course this notation means that we should do something. And when you are seeing this kind of notation, I guess like you should be having some alarm bells ringing in your mind that, okay, there's some index I, what on earth is this index and what should I do with it? And then when you say see two indices, then you remember that maybe this is Einstein's summing convention and I should progress accordingly. So index I appears twice, and the notation then says that, okay, there's a summation already implied, and we do not then need to be actually writing the summation out, but rather we can just skip it all together. And this is extremely nice when we are dealing with the more complicated vector identities, and for example, if you would want to derive them. So like I already said, I started, this notation is not the core content of the course, but it really helps if you would, for example, want to derive these different algebraic properties and identities of vectors, or what we have in the vector calculus. So it's actually quite useful. And I would have enjoyed if my physics teacher or math teachers would have shown me or mentioned me of this kind of summing convention and the notation before I was 30 something. I was never informed, and I'm so mad about it. I'm not happy because it would have helped quite a bit of my journey of becoming more knowledgeable on these things. Okay, so like I promised, we can also have a compact notation for the vector product. So when we have the vector product of two vectors u times v, if we would want to write it down using summations, and we could do it by just introducing Levi-Civita parity symbol, we would end up having three summations. And now we have three indices, and we have this kind of epsilon ijk. This is Levi-Civita parity symbol. I will introduce it later, what it is. And then I'm multiplying uj with vk, and then I'm having a component along I direction. So E hat is a unit vector along x, y, or z direction, depending on whether I is 1, 2, or 3. And now, since I have many indices in here, so I have one I index in here, and I also have, I have I index here, and I have a second I index here, so I have two I indices. So I can skip writing this summation out entirely because I can use Einstein's summing convention. Then I have my J index here, and I'm also having a J index here, so I can remove also this summation convention. I do not need to write it because I have two indices of J's, and the same thing for K's here. I have two K's, so I can also skip this summation. And this is now actually that we are starting to see the benefit of Einstein's summing convention, because we can just write the dot product simply that it's the Levi-Civita parity symbol epsilon ijk times uj times vk times e hat I. And here epsilon is the Levi-Civita parity symbol, and this is defined simply that depending on the indices, if I'm having indices of ijk and they are either 1, 2, or 3, so x, y, z, or 2, 3, 1, so y, z, x, or 3, 1, 2, the Levi-Civita parity symbol gives me a number of 1, and it gives -1 if I'm having reversed indices. So if I'm flipping the indices differently, so I'm just having 3, 2, 1, or 2, 1, 3, or 1, 3, 2 indices, then I'm having -1 as my Levi-Civita parity symbol. And in other cases, if any of those indices is equal to another one, then I'm having a 0. So this is what I have here. So it looks awful, but it really helps if I would want to do some derivations, because then I could quite simply write, for example, a vector product using this kind of term. And this really helps in derivations, trust me. So let's verify the usefulness of Levi-Civita and the summing convention. So let's just really try to calculate what is this ux, the cross product of u and v. So the first term, like what we get out, let's look first at the x component of this cross product. So let's first have the e hat 1 here, and then what's inside, like what do we have pointing along the x direction is that we have u2 times v3 minus u3 times v2. So this is of course what we know from another way of calculating the vector product, but let's verify how this works. So we have the summation, we have three summations here. So I'm starting to sum the I index here. And the first index gives me I1 hat. So basically the unit vector along x direction. I could just have x hat here. And then the Levi-Civita parity symbol gives me the rest. So basically I have my j, k terms here, and I'm summing over the different terms. And since all the other terms where the indices are not all different, I have zeros. So only thing that is left is that I have my I index of 1. So I'm just looking at this term and I'm writing out that, okay, I have my 2, 3 indices. My Levi-Civita is +1. I can write this one here. And then I have the second term that is left. So I have this 1, 3, 2. And that gives my -1 in here. And I'm just having this minus here. So this is how I can calculate things. And I can now progress. I will do the same. I will do the next summation. I now equals 2. So I have E2 hat. And then inside the parentheses, I have these two terms. And let's now verify that indeed this is the case. So I have I equals 2. So I'm now looking at this term, for example, I equals 2. And then I have 3 and 1. Levi-Civita gives me unity. So I have 3 and 1 exactly like this. And the second term is that I have 2 and I have 1 and 3, and now Levi-Civita gives me -1, and this is the term indeed, and all the other terms are zeros because of the Levi-Civita properties, and then the final term for the I equals 3 case, and I have this term. So please verify it yourself. You can also do this same thing by just looking from the Wikipedia that how do I calculate the cross product, but you also see that you can also use the Levi-Civita parity symbol and also simplify things using the Einstein's summing convention. And this is the right form, so it really does work. And this is nice because if you would need to generalize things, this is the right approach, I would say. Trust me on this one, if on nothing else. Sometimes we end up with something even more complicated. So instead of just multiplying 2 vectors, we may multiply 3 vectors together. And then there are 2 different possibilities. So either we can have a so-called scalar triple product, which is basically written that we have 3 vectors. So U1, and then we have U2 and U3. And we have possibility that we are first calculating the cross product of vectors U2 and U3. And then we are calculating the dot product with vector U1. And then this is essentially, if you would want to calculate this, you would calculate the determinant of this kind of vector or matrix looking thingy, so that we would calculate the determinant of U1, U2, U3. And this is also known as the scalar triple product. Arising from the fact that we actually indeed do have a scalar valued number out of this kind of calculation. Please remember that the final operation we do is a dot product, so it makes sense that we have a scalar out. Another possibility is that we have a vector triple product, so that we can multiply 3 vectors together, and now all the multiplications are done using the vector product, so cross product, and the result of this looks something like this. So we have the dot product of vector v1 with the v3, and then I'm multiplying this with v2. So please remember, dot product gives me a scalar. So I have a scalar multiplying v2, so nothing strange here. And then the second term will be minus the dot product of v1 times v2 and v3 here. And this is known as the vector triple product. And please note here, the output is a vector valued quantity. So I have my vectors v2 and v3 here. And already we see that this looks quite formidable, that how I could verify that this indeed is how things are calculated. And I really recommend that if you want to verify this, use Levi-Civita parity symbol and the Einstein summing convention, and you see that this is the truth, that this is how you calculate vector triple products. And now we are ready to actually move into vector calculus. And this is what we want to do, because we want to take use of Maxwell's equations and form a full vector differential equation. And how do we progress is that we define a scalar valued function phi and a vector valued function e, and it's not a coincidence that they look like a scalar potential, phi, the notation, and E like a vector field. So here we just define new functions, and now these are not constant valued numbers anymore, but they really are functions. So that the value of this scalar valued function phi really depends on the location, and here the value of this vector valued function E really depends on the location. And please already remember this when we are going into the next lecture, that this notation here, that we have a phi here, it's not a coincidence. So there is really essentially could be understood to be the scalar potential of a potential formulation of electrodynamics, and here this really could be introduced and understood to be the vector E field of my electromagnetic radiation. For example, if you want to connect these functions with something physical. What we must also assume, and this is of course because we are doing calculus, so that we must have functions that are differentiable, and we assume that these functions we're dealing with, they're continuously differentiable. So what that means, it's a mathematical term, it just means that we can find derivatives for these functions in each of these points, and in continuous manner, so that there won't be any discontinuities in finding these derivatives. So this is what it means. And this is what we in physics always pretty much assume out of our functions, because in nature we really don't have that much of discontinuities present. Of course, sometimes in some math we do have discontinuities. Like, I don't know, example I guess would be, I'm thinking of Van Hove singularities when I'm calculating the density of states for an electron system in a 1D case, or phononic density of states in a 1D case, but let's not go there. Most of the time you really do not need to worry about non-smooth, not continuously differentiable functions. But when we have something, a function that is representing something physical, really the good assumption is that it must be continuously differentiable. And since we know that we have a wave function in the end, this we should also have twice continuously differentiable functions, but more on that later. And now with these two functions that we have defined, so the phi and E, we many times encounter these kind of vector calculus operations. So we for example need to calculate the gradient of my scalar function phi, and how that is being defined is that we calculate the partial derivative of my scalar function phi with respect to x, and then this points along the x direction. And then I have a second component, I'm calculating the partial derivative of my scalar function phi with respect to the y coordinate, and then this points along the y direction. And then the final thing, of course, is to calculate the partial derivative with respect to z, and that points along the z component. So gradient operator of a scalar function is being defined like this in a Cartesian coordinate system. And this gives me a vector valued function. Please note that we have x, y's, and z's in here, so I really do have a vector output when I'm calculating the gradient of a scalar valued function. So please note here, phi, this is a scalar valued function. It gives me a scalar, and when I'm calculating the gradient, I'm actually getting a vector out. So please note that these kind of changes in the type of my function may start arising. I can also calculate the gradient, of course, why not, for a vector valued function. But interestingly enough, this does not give me a vector anymore, but rather even something more complicated. So in fact, it actually does give me a matrix, or at least something resembling a matrix. I guess some mathematicians, they would say that it's not a matrix, it's a tensor, but let's not go into those subtleties. It looks like a matrix, so let's just say as a physicist that it is a matrix. So this is a gradient of a vector function, and this is how we would define it. So we would give a 3 times 3 matrix out. So I would calculate in the ij matrix location the partial derivative of my given components, given component, my function's given component with respect to the different variables. So I can have, for example, Ex here, and I'm calculating the partial derivatives of either x, y, or z here, and I will get the different matrix components out and so forth. And sometimes people say that this is the Jacobian matrix, so that if you encounter that kind of terminology, you know that essentially I'm calculating the gradient of a vector function. Here, this is what we call divergence of my electric field or E function, vector valued function. And how I calculate the divergence is that I calculate the partial derivative of my Ex component with respect to X variable. I'm summing this with the partial derivative of the Ey component with respect to the Y coordinate, and then I'm summing this with the partial derivative of Z component with respect to Z. So this is known as the divergence. And the similar thing here, I have my curl operator, so I'm calculating a vector product with the nabla operator on E, and here I'm actually getting a vector out. So the curl of an E field is defined, and here I'm using the Levi-Civita parity symbol again and Einstein's summing convention. So here I'm just taking the partial derivative of Ek with respect to xj, and then I'm having a vector pointing along the Ei direction. So this is known as the curl. And the Jacobian matrix Eg is essentially a 3x3 matrix. So a point of notice here. Here I'm having divergence. E, this is a vector valued function, but when I'm calculating the divergence, as we can see, this is a scalar valued quantity, so that the divergence gives me a scalar out. Curl, this gives me a vector. Please note here that I have my hats here, and please note that for simplicity, I'm using Einstein's summing convention, so that I have actually 3 summations in here when I want to calculate the curl of my E field. So I have I here once, twice, j here once, twice, and k here once and twice. So in fact, I have 3 summations when I'm wanting to calculate the curl operator. And I have a vector out. Okay, we're almost done. Still one more slide to left. And let's now generalize our treatment to the second order derivatives. And this is, of course, why we want to do this, is that the wave equation is a second order differential equation. So we should also just have the math ready for that case that we're actually writing the wave equation in 3D case using vector notation. So here, for simplicity, we assume that our functions phi and E are smooth. Smoothness just means that it has all the derivatives of up to all orders. So then definitely these functions also have the second order derivatives. And I'm being a sloppy physicist, so I'm just assuming more than is absolutely necessary here. So of course, the functions do not need to be smooth. It's a way more stricter criteria that we need. We only just need that we have the second derivatives also, so that they are twice differentiable. But somehow it's easier to write that the function is smooth than to say that it's twice differentiable. So now I can define a Laplace operator. So now I have my triangle pointing upwards, and this basically notation means that I have the 2 triangles going upwards, downwards, and I'm calculating my scalar function phi here. So what these triangle operators, what they actually mean is that I'm first calculating the gradient of my scalar valued function phi, and once I'm done calculating the gradient, I get a vector out. I'm calculating the divergence of my output. So this is essentially what the notation means here. So I have my scalar valued function, and I have my Laplace operator. So first I'm calculating the gradient, and then I'm calculating the divergence of the gradient. And this actually is quite simple in the end. So basically I'm just summing the second partial derivatives like this, as we already encountered earlier. And this is known as the Laplace operator. So we really don't need to calculate the gradient first and then the divergence. We can just use this equality here. So we just calculate the second partial derivatives and we sum them together, and that's it. This gives me Laplace of a scalar valued quantity. Then I can do the same thing. so for a vector valued function, so I can also calculate the Laplace on or operate on Laplace operator on a vector valued function. And the notation up until this point is exactly the same, but now the actual calculation is different. So because E is actually a vector valued function and not a scalar valued function, what we must actually calculate is that we must calculate the divergence of the E field, and then we calculate the gradient, and then we subtract from this guy a double curl of the E. And this is known as the vector Laplace operator. This is also sometimes known as the Lagrange's formula, more on that slightly later. But this is a kind of operator we must do quite a few times during this course, because we end up with this kind of operator when we have a three-dimensional wave equation formed for a vector valued function. So this is what we must calculate when we are solving the wave equation shortly in chapter 4. And then what we have also, when we are going into the vector calculus, we have a few identities, and these two that I will be showing to you are the most useful for this course, is that when we calculate the gradient of my scalar valued function, so I'm calculating the gradient of phi here, and then I'm calculating or trying to calculate the curl of this gradient out, I'm always getting a 0 out. So this is an identity and known as the curl of a gradient, and that's identically 0. If you would want to get some kind of physical understanding why this is the case, I'm calculating the gradient. So basically I'm getting a vector field out that is pointing outwards from my origo, from my location of origin. And then with calculation of a curl, I'm somehow I'm calculating how curly the vector field is. So how much it rotates around my center of origo. And since I'm calculating a gradient field first, where the vector field points always exactly outwards or inwards from the origo, and then I'm trying to calculate that how curly this kind of field is, I'm always getting a 0 vector out, so that there's no curl of a gradient field. And then another identity is that if I calculate the curl of a vector valued field, so how curly it is, or how much it seems to be rotating with respect to the point of origin, and then I'm calculating the divergence of this curl, I'm always getting a 0 out. And this is known as the divergence of a curl. So this guy here physically would give me a kind of a field that tells me how much this field E rotated with respect to the origin. And then I'm trying to calculate the divergence. And divergence means that if I'm, for example, physically, I'm thinking like a physical interpretation for here, that if I would draw a circle centered at the origo, and I'm thinking that how this vector field of interest, how that would go through the spherical circle, and nothing would go through when I'm calculating I'm having this kind of curly field, so that my divergence will be equally 0. This is probably not very clear things for now in a lecture. I recommend that you think about it, and please ask me or the teaching assistants during the course that could you please repeat what was the physical meaning of these. But in fact, there is a quite good physical meaning behind these identities, and they can be explained. So when we have time and we're really meeting up, then we can show with pen and paper that what I was trying to say here. Nothing complicated here in the end. It just takes a while to kind of grasp what I'm trying to say to you. And the final thing I wanted to show and say is this: I already mentioned that the vector Laplace operator, it's also known as the Lagrange's formula. So this is a kind of mathematical quantity we must calculate quite a few times during our course. So we take the double curl of the E field, and this can be calculated that it's the gradient of a divergence of the E field minus the vector Laplace of the E field. And as you can see here, I'm basically just changing the terms here of my vector Laplace operator. So instead of solving this vector Laplace, I'm now solving the double curl when I'm calculating the Lagrange's formula. But this is what we are using quite a bit in our course. But basically, it's exactly the way we define the vector Laplace operator. So now we are done. You know everything about vector algebra. You know everything about the algebraic properties of vectors, and you know the basics of vector calculus. And I know this looks awful to you, but in the end, you get the use of it, and they're not that complicated. You just go back into these slides and try your best to memorize them and use them accordingly as we have introduced here, and you will be perfectly fine. And please remember the final thing, that always when you're dealing with math, try to keep in mind that is the physical quantity that you're trying to describe and you are describing, is it a scalar or is it a vector? And that might also help a lot of getting rid of the confusion of how the math should look like. So if on the left-hand side of your equality you have a scalar, then you know that also on the right-hand side you should have a scalar. And if on the left-hand side you have a vector, then on the right-hand side you should also have a vector. And if you remember these two rules of thumb, you are already getting like the winning side of many things. So please remember this. I thank you for your time, and please join me soon to listen for my last lecture on this chapter 3. Thanks, and bye-bye.